Radio astronomy begins with an awkward fact. The universe is shouting in wavelengths our eyes cannot see. A dish gathers those faint radio waves, reflects them toward a receiver, and turns their tiny electrical traces into measurements that astronomers can study. We are here to determine the GOAT of greatest all-around, single-dish radio telescope of the 20th century. The field is greatest all-around single-dish radio telescope of the 20th century. Diameter matters because a larger collecting surface can catch weaker signals, but a giant dish that cannot point accurately, hold its shape, reject interference, or accept better receivers becomes an impressive monument with a very limited research program. So, this is not a contest for the widest bowl. The field is the greatest all-around single-dish radio telescope of the 20th century. The instrument that combined discoveries, useful sky coverage, adaptability, durability, and service beyond ordinary astronomy. The challenge became possible after wartime radar had produced powerful transmitters, sensitive electronics, and engineers accustomed to steering radio beams. Astronomy then asked them to reverse the process and listen, patiently, for signals arriving from across the cosmos. A movable dish can weigh thousands of tons, yet its reflecting surface must remain close to the intended curve, while gravity pulls from a different direction at every angle. The machine has to behave like both a bridge and a precision optical instrument. The receiver matters just as much as the steel. New electronics can open fresh frequency bands, lower internal noise, survey several points at once, or connect a dish to distant partners so that separate antennas behave like one much larger telescope. That is why the strongest candidate must survive changing science. Pulsars, interstellar molecules, quasars, planetary radar, spacecraft communications, and short-lived cosmic bursts all demanded different hardware and different ways of observing. 4 machines make the final comparison. One mastered equatorial tracking. One proved that a huge dish could be fully steerable. One refined that idea at 100 meters, and one traded freedom of movement for extraordinary collecting area. Green Bank's 140-foot telescope began with an engineering warning that may have saved it. Inspectors found more than 70 small cracks in a crucial bearing design. In a cold West Virginia winter, brittle fracture could have brought down the entire instrument. The redesign delayed completion until 1965, but the finished telescope gained a rare advantage. Its equatorial mount followed the sky around an axis aligned with Earth's rotation, allowing smooth tracking even near the point directly overhead. It then helped pioneer very long baseline interferometry. In 1967, data from Green Bank and ever more distant antennas were combined to imitate instruments hundreds, then thousands of kilometers wide. Resolution no longer had to be limited by one physical dish. It also opened doors in astrochemistry and remained a general astronomical instrument until 1999, before returning for ionospheric work, satellite reception, and pulsar monitoring. Its career was resourceful and technically influential, although its scientific reach never became as broad as the giants ahead. At Jodrell Bank, the Lovell telescope answered a more audacious question. Could a dish, about 76 meters wide, be pointed almost anywhere? Bridge engineer Charles Husband and astronomer Bernard Lovell produced a fully steerable machine many experts had considered impractical. When it entered service in 1957, it was the largest steerable radio telescope on Earth. Almost immediately, it tracked the carrier rocket of Sputnik 1, making an abstract Cold War announcement detectable as a real object moving through space. The instrument went on to track probes and contribute to work on quasars, pulsars, black holes, gravitational lenses, and the faint microwave afterglow associated with the early universe. Its importance lies partly in proving what the whole field could become. That pioneering status also exposes its limit in this comparison. Much of its greatness is architectural and historical. It made the giant steerable dish credible. Its later science remained significant, but another European instrument would execute the same basic idea with greater scale and precision. The Effelsberg telescope opened in 1971 and entered full operation the following year. At 100 meters across, it pushed the fully steerable dish close to the practical limit, while remaining accurate enough to observe wavelengths far shorter than its enormous size suggests. Its engineering achievement was not simply that it moved. The telescope had to preserve a useful reflecting shape as gravity shifted across the structure, then guide incoming radio waves into receivers designed for bands from long centimeter waves down toward millimeter wavelengths. Effelsberg became a dependable research platform for pulsars, molecules, magnetic fields, galaxies, and international interferometry. Continuous upgrades to its surface, electronics, receivers, and control systems kept it among the world's most capable single dishes long after its inauguration. For pure steerable dish engineering, Effelsberg is extraordinarily difficult to beat. Yet it arrived after the decisive pioneering phase, and its public record contains fewer moments. When one instrument crossed repeatedly between frontier astronomy, planetary missions, mass communication, and new survey methods, Arecibo chose a different bargain. Its 305-meter reflector was built into a natural hollow in Puerto Rico. The dish itself did not turn. Suspended equipment moved above it, granting limited sky coverage in exchange for immense collecting area. That bargain paid spectacularly. Russell Hulse and Joseph Taylor used Arecibo to discover the first binary pulsar in 1974. Its changing orbit later provided evidence for energy loss through gravitational radiation, work recognized with the 1993 Nobel Prize in Physics. Arecibo also worked as a planetary radar and an atmospheric instrument. It mapped nearby worlds, studied asteroids, examined the ionosphere, and found the first planets known beyond the solar system, orbiting a pulsar rather than a sun-like star. Its sensitivity gave it access to signals that smaller dishes struggled to detect. Its suspended platform and fixed reflector also made it visually unforgettable. Few scientific instruments have ever looked so much like a machine built to interrogate the universe directly. But the same architecture constrained pointing and concentrated enormous loads in cables and towers. In 2020, support cables failed progressively over 4 months. The platform finally fell into the dish, ending the Great Telescope before a controlled retirement was possible. Arecibo is the strongest rival because its best science was monumental. It wins on collecting area, radar capability, and several discoveries of Nobel-class consequence. It loses ground only when the question expands from peak power to adaptability, accessible sky, operational continuity, and range of service. The GOAT is the Parkes Radio Telescope, now also known by its Wiradjuri name, Murayung. Its 64-meter dish was never the largest in the world. What it mastered instead was the art of remaining useful as the questions changed. Inaugurated in 1961, Parkes was fully steerable and placed under the rich southern sky. From central New South Wales, it could study regions near the center of the Milky Way that pass high overhead, where pulsars and dense clouds of gas are especially plentiful. The original structure proved unusually receptive to reinvention. Enders replaced surfaces, focus equipment, receivers, computers, and control systems, while the main steelwork kept turning. Continuous upgrades eventually made the telescope more than 10,000 times as sensitive as it had been at the beginning. That distinction matters. A radio telescope is not one finished machine. It is a platform carrying whatever the best current receiver can hear. Parkes aged less like a monument and more like a durable laboratory whose most important instruments could be exchanged without rebuilding the entire site. Its public fame came from Apollo 11, but the precise story is better than the legend. Honeysuckle Creek supplied the first television pictures. 8.5 minutes later, NASA selected the stronger Parkes signal for the next 2 hours and 12 minutes of the moonwalk broadcast. The telescope was working in severe wind, beyond its normal safety limits, while hundreds of millions watched. It did not single-handedly televise the landing, yet it delivered most of the pictures from humanity's first steps on another world when reliability mattered in public. Spaceflight support was not a one-night performance. Parkes tracked Mariner 2 during the first successful planetary encounter in 1962, later supported deep space missions, and in 2018 and 2019 helped follow Voyager 2 as the spacecraft crossed into interstellar space. Astronomy, however, supplied the deeper case. Early Parkes observations helped establish the nature of quasars and revealed the Milky Way's magnetic field. In 1973, Observations exposed the Magellanic Stream, an enormous trail of hydrogen associated with our neighboring dwarf galaxies. The decisive transformation arrived in 1997 with a receiver that watched 13 patches of sky at once. For survey work, it multiplied the telescope's view without enlarging the dish, converting a mature instrument into a discovery machine for an entirely new generation. That multi-beam system found more than 900 pulsars, and for a time, helped Parkes account for nearly half of all known examples. A pulsar is a compact neutron star whose rotating radio beam sweeps past Earth with clock-like regularity. Among those discoveries was the first known double pulsar system, in which both neutron stars are visible as pulsars. Their rapid orbit created an exceptionally clean laboratory for testing general relativity where gravity is far stronger than in the solar system. Parkes also supplied the archival data in which the first fast radio burst was identified in 2007. These are millisecond flashes from far beyond our galaxy. The telescope had recorded a new cosmic phenomenon before astronomers even knew what category of event they were seeing. Large surveys mapped neutral hydrogen through the Milky Way and found more than 2,500 previously uncatalogued nearby galaxies. Here, the value of the instrument was not one dramatic signal, but its ability to collect coherent maps across huge portions of sky. Arecibo still beats Parkes in raw collecting area and in several singular achievements. Effelsberg exceeds it in diameter while remaining steerable. Lovell carries the stronger claim to having invented the public image of the giant radio dish. Parkes does not win every category. Its limitation is real. A 64-meter reflector cannot gather the faintest signals as quickly as a 305-meter one, and modern arrays can produce sharper images. The verdict depends on the stated field, not on pretending one telescope is universally supreme. Within that field, the balance is decisive. Parkes joined frontier astronomy to spacecraft tracking, broad southern coverage to precise steering, a durable structure to repeated electronic reinvention, and famous public service to discoveries that created new areas of research. Murray-Young earns its GOAT status because radio astronomy's greatest all-around dish was not the one that listened hardest for a single era. It was the one that kept learning how to hear more of the universe.